All right, so today we're going to be applying the hypothesis testing that we covered yesterday. So what the problems are going to ask you to do is to state the null and the alternate hypothesis, to find a test statistic, to find the p-value, compare it to a level of significance, and then make a conclusion about what is going on. So I'm going to walk you through all of those steps today with this example that's found in your textbook. This is about Rosie, who is an aging sheepdog. She's brought to the vets and they check her vital signs, and what's trying to be concluded is whether or not the vet should say that Rosie is healthy and perfectly fine, or perhaps that her heart rate is beginning to slow, which may mean that she is nearing the ending stages of her life. Which is pretty important to a pet owner because you kind of want to know, like, is my dog okay, or are we starting to needing to think about different things? So at the end of this problem, we are going to be able to say with a certain level of confidence whether or not we think that Rosie's heart rate is slowing down, or maybe we can't say that and we're just going to stick with the known value of that her heart rate is just fine. So that information is what's going to allow us to create our null and our alternate hypotheses. So Rosie's an aging sheepdog. From the past experience, the vet knows that this breed should have a resting heart rate of about 115 beats per minute, BPM, with a standard deviation of 12 beats per minute. Over the past 6 weeks, Rosie's heart rate was measured, and the measurements were 93, 109, 110, 89, 112, and 117. So keep in mind, these should all be on average around 115 beats per minute. So I'm noticing a couple low values. I'm noticing a higher value, and then some that are right around 115. So whatever this average may be, can we say with a certain level of confidence that her heart rate is slowing? And so that's our big question that we're asking. So I'm first going to write out some things that we know and what we need to know in order to successfully answer this problem. So first of all, what we do know is we do know the population mean and the population standard deviation, meaning we know what her heart rate should be by past experience, and we also know what it should be within a certain amount. What we need to know is what is her average heart rate. We need to know what is the test statistic. So that is going to be the deviations above or below the mean. And then we're going to use the normal distribution to figure out the p-value. Now, just as a reminder from yesterday, the formula to find the test statistic is going to be the x value that we are referring to. So this x value is going to be the x bar minus the mean, which is 115, divided by the standard deviation, which will be divided by the square root of the sample size. Now, my sample size is going to be 6. Once I figure out that test statistic, I am going to throw it into the normal distribution, again on Google Sheets. And that's going to be the test statistic, 0 and 1. Now, the reason why I'm using 0 and 1, just as a reminder, is that the test statistic, since I am converting it to a z-score, it is a deviation from the mean. Whenever we want to do the normal distribution working with deviations, we have to assume that the mean is 0 deviations away from the mean, meaning it hasn't gone anywhere, it's right at the mean, and that every deviation, every set deviation is 1 unit apart. So when we do the normal distribution, it's going to be our test statistic, which we have to calculate, and then comma 0, comma 1. And remember, it's going to have to be that true or false. As a heads up, it's always going to be true because we are finding a range. We're not going to find right specifically at that value. So if you have been confused, I didn't even write it this time, it's just going to be true. Now I want to take a little sidebar here with the p-value. Something that I didn't talk about yesterday that they're going to ask you in the book, but I don't need you to comment on it, is it's going to ask, is it a left-tailed, a right-tailed, or a two-tailed test? Now, these tests are determined by what our alternate hypothesis is. Now, if we think that our sample average is below the mean that we know, that is a left-tailed test because it's everything less than. Now, if it's less than, I'm just going to do the equal norm distribution of whatever that test score is, 0, 1. If it was saying that I think that Rosie's heart rate is faster than what we know to be true, that's going to be a right trail because it's going to be greater than. So if it's greater than, once I find that test statistic, I am going to have to do 1 minus. And then if it's a two-tailed test, meaning I'm just saying it's something different than 115, it could be less, it could be greater, I don't know. I just don't think it is 115. By saying that it could be less or it could be greater, we now have two tails to deal with, meaning whatever probability we find for the equals normal distribution of our test score 0, 1, we are going to want to double that probability of happening to find our p-value. So each of these normal distributions find the p-value that we are going to compare to our level of significance or our alpha in these problems. So here are my two hypotheses. The first is going to be that the null hypothesis is that the heart rate is 115 beats per minute. That's just what I know to be true. Due to Rosie's measurements, I am thinking that her average is somewhere below 115 beats per minute. So we think that Rosie's heart rate may be decreasing based off the numbers that we witnessed. It's now our job to conduct a test so that we can say whether or not Rosie's heart rate is definitely slowing down or not. Now to do that, I'm going to head over to Google Sheets. Now what we have here is over here is going to be the 6 measured values, the vital signs. And I wrote in the known mean, which was 115 beats per minute. I wrote in the known standard deviation, which was 12 beats per minute. And I calculated Rosie's mean. Now Rosie's mean, I did equals and the command average, and I highlighted this column, and it gave me an average heart rate of 105 beats per minute. My null hypothesis was that it was 115, and I reminded myself that the alternate hypothesis is that I think that Rosie's beats per minute is less than the expected beats per minute that we have traditionally followed. So I'm going to find my test statistic. I did that by doing the equation that was found in the slide. So I'll go back to it. This equation right here is what I used to convert to find the deviations from the mean. So the D5 minus D2. So that was the sample mean minus the known mean divided by, notice all the parentheses, the standard deviation of 12 divided by the square root of the sample size of 6. You will need these parentheses because, again, PEMDAS, order of operations. If I just had D5 minus D2 divided by 12 divided by the square root of 6, Google Sheets is going to say, all right, I'm going to do all multiplication division first. So it's going to do D2 divided by 12. That quotient will get divided by the square root of 6. And then after you did all that division, it's going to subtract it from D5. We don't want that. We have to be conscious of those parentheses. So the numerator is in parentheses and the denominator is also in parentheses. So they know, hey, do the numerator first, do the denominator second, and then divide the two. So my test statistic is negative 2.0412, yada, yada, yada. What does this mean? That means that the average heart rate of our sheepdog, Rosie here, was over 2 deviations below the expected value. That's not good. That means that she's well outside, like 97.5% of other sheepdogs. So it is pretty low. Well, let's go ahead and figure out the p-value. Now, since it's less than, that means that I'm going to just do the equals of the normal distribution. It's a left-tailed test. So I went ahead and I used my test statistic found in D11, the negative 2.04, comma 0, comma 1, comma true. And that gave me 2%. So what does this p-value mean? Well, this p-value is going to be the probability of a type 1 error. So what that means that there's a 2% chance that it could be, that I could say, hey, her heart rate is slowing down, And in reality, I was wrong and her heart rate's fine. So that's type 1, because even though I'm warning the owners, hey, your dog may be starting to pass on, then you feel sad. You start to accept that. Maybe you give Rosie a few extra treats, and then she lives for a few more years. Yeah, you were wrong, but you still have your dog. Type 2 would be like, nope, Rosie's good. You wake up in the morning and or dog. That would be really bad. So type 1 versus type 2. So the conclusions that we can make. So in this problem, it didn't give us an alpha or a confidence level. So I made this up. So I said that if we were to say something with a 95% level of confidence, that means our alpha was 5%. So there's a 5% chance that we are wrong, a 95% chance that we're right. See how that kind of works? If I said that I wanted to be 95% confident, that means that I would be willing to risk being wrong up to 5% of the time. So I am willing to tell these patients that their animal is dying when it isn't, only 5% of the time. If there's a higher chance of me saying the wrong thing, then it's not worth me letting these people know that their animal is dying. If it is lower than 5%, so if it's within my margin of what I'm willing to be wrong in, then I will make that conclusion. So when I compare 2% to 5%, 2% is less than 5%. So that means I'm within my willingness to be wrong. So I can say with a 95% level of confidence, we can reject the null hypothesis. So I am rejecting the fact that I'm saying that the heart rate is 115 beats per minute. And instead, I'm going to assume that Rosie's heart rate is indeed slowing down. Now, I can't conclude how much it's slowing down by, or how drastic it's slowing down, or how much time she has left to live. I am just saying, hey, her heart rate is slowing down. We'll have to do more tests to figure out what's going on. So that's the only conclusion we're making. We're just rejecting that her heart rate is 115 beats per minute. We're rejecting that, and we are assuming it is something less. Now, if I were to change my level of confidence, what if I was 99% confident about this? That means I'd only be willing to be wrong 1% of the time. That's pretty strict on yourself, but you hold your word with integrity and you do not want to be wrong. You're only willing to be wrong 1% of the time. Now, if that was the case, our p-value is 2%, which means it's greater than 1%. Now, that is too high of a risk that you're willing to take. So that's going to change the way you interpret this information. You would now say with a 99% level of confidence, that's a typo. With a 99% level of confidence, we do not reject the null hypothesis, and we cannot assume that our heart is slowing down. So I'm going to go out there and say, hey, like, yes, the heart rate is lower, but I'm not worried enough to say that we should say that her heart rate's slowing down. For now, Rosie's fine, but maybe come in a couple of months and let's check her again, and we'll see if the heart rate's still there, and maybe we'll conduct this test again. So I'm not saying that her heart rate's slowing down, but maybe it's going to be on my lookout. Maybe it's on my warning list of maybe we should keep an eye on it, but let's not worry about anything yet, but let's keep an eye on it. So that's how we can conclude something with numbers, just based around what we see and comparing it to what we know. Now in sheet 2, I did a quick example of another problem in the book of what would be more than, and I just want to show you kind of the differences between a less than and a more than. I'm not going to get into the in-between because honestly, we're running out of time, and I want to make sure we get to the things that are most important to our performance-based assessments rather than every type of example that could occur. So these were dealing with stocks. They were percentages, so this is 5.7%. Notice how I didn't convert it into a smaller decimal. I just kept it as the percent and said the percent was my label. I didn't convert it to decimals. And so my average was about 5.38. I went ahead and I found my test statistic. So I took the average of 5.38, I subtracted the known average of 4.7 from it, I divided it by the known standard deviation of 2.4, and I divided that by the square root of my sample size, which was 10. So my test statistic was 0.89. Now, my test statistic is the deviations from the mean. So that means that this average of this stock portfolio was about 0.9 deviations above the mean. So it's pretty good. But can I say with a certain level of confidence that this portfolio is higher than where I expect to be? So if I were to then report out to all my investors, can I say with a certain level of confidence, this portfolio is higher than where we normally are? Let's keep pursuing this. So you're going to go ahead and do the math. Now, I know that 0.89 is above the mean. So that means that my probability of it occurring should be less than 50%. If I was at the mean, 50% is below, 50% is above. So if I am already past the mean, the probability of this occurring should, being more than that, that is, should be less than 50%. So if I accidentally do the normal distribution and I didn't do the 1 minus, I'm getting a probability of 81%. That's more than 50%. I know that if I'm calculating more than this z-score, then if I'm more than this z-score, it should be less than 50%. So I corrected myself and I did 1 minus, and now I have a probability that's more accurate. Now let's take a look at this p-value. If I wanted to be, again, I'm talking to a room of investors, and I wanted to be 95% sure that this is the place we need to be, this is the portfolio we need to pursue. That means that I would have to have a chance of making an error no more than 5% of the time. This p-value is 18.5%. That means that there's an 18.5% chance that I am saying, yes, this is better, let's invest, when it's not better. It might be around the average, maybe it'll be slightly higher, but it's not high enough to bring us to a new tier of investing. So it would be an error because we probably won't lose money, but we're not going to gain the money like we should have. And if we only have so much capital, we can only invest it in so many different portfolios that maybe because you listened to me, that you missed out on the portfolio you should have invested in. So this would not be a low enough probability of a type 1 error for me to say that, yes, this portfolio is better than what we expect from other portfolios. So my conclusion here would be that I cannot reject the null hypothesis, and we cannot say that this portfolio is better or yields a higher profit than what we would expect from another portfolio. So that's kind of just the differences of the two. Sorry for the longer presentation, but we're running out of these, and I really want to get the bang for your buck here, so I'm just going to keep talking. No. Anyway, if you have any questions, feel free to come into the Zoom. I'll be here looking to answer any questions. I will give you more of an update on your final and how finals are, again, when I know what we're doing. If we're going to have 2 weeks of finals, that's going to change things opposed to if we have 1 week of finals. So today or tomorrow is when I should know what's happening. We'll see. But until then, I'll see you when I see you.